We're going to take a look at what it means for a function to be even or odd. But in order to do that, we have to understand something about symmetry. So let's take a look at what it means to be symmetric with respect to the y-axis. If I were to choose a point, say the point 5, 5, and I were to ask you to locate another point that would be symmetric with respect to the y-axis, to the point 5, 5, you probably would go straight over here until you got to the point negative 5, 5. If we picked another point, say 2, 2, you would choose the point negative 2, 2. And if we picked the point 0, 0, that point would be symmetric with respect to itself. There are graphs that you've seen that have this kind of symmetry. One of them, for example, is the graph of y equals the absolute value of x. Another that you are aware of is y equals x squared, the parabola. These graphs are symmetric with respect to the y-axis, and graphs that have that kind of symmetry, or functions whose graphs have that kind of symmetry, are called even functions. We'll take a look at that a little bit further in just a moment. Let's take a look now at what it means to be symmetric with respect to the origin. So again, I'll pick a point, let's say the point 2, 8. And I would like to find a point that is symmetric with respect to the origin. That means that if I went from this point through the origin and continued down, the origin would be the midpoint of that line segment. And that would occur at negative 2, negative 8. If I pick the point 1, 1, and I were to continue through the origin, the companion point for that would be negative 1, negative 1. These points, these point pairs, are symmetric with respect to the origin. A graph that you're familiar with that has this kind of symmetry is y equals x cubed. Graphs that have symmetry with respect to the origin are called odd functions. And that's easy to remember because odd and origin both start with the letter O. Here is a function, or here is a graph that has neither symmetry with respect to the y-axis. This is shifted a little more to the left, so it's not really symmetric with respect to the y-axis, and it's clearly not symmetric with respect to the origin. In terms of categorizing these functions, or these graphs, we'll either call them even, or odd, or neither. And we need to figure out how can we determine, without actually graphing them, whether or not they have one kind of symmetry or the other. So let's take a look at what all of this means when we look at the functions themselves. First of all, we talked about, in order to be symmetric with respect to the y-axis, if we chose a point, 4, 6, the point symmetric with respect to the y-axis would have been the point negative 4, 6. In other words, all we did was we replaced the x-coordinate with its opposite. The y value stayed the same. So that's what we're paying attention to. Replace the x-coordinate with its opposite, and the y value stays the same. In notation, we're looking at what happens when we take a y value, f of x, and we replace the x value with its opposite. The y values should remain the same if it's symmetric with respect to the y-axis. So here's the function we dealt with, y equals x squared. Replace the x value with its opposite, do the algebra, and we find out that the y value is exactly the same as the one we started with. Therefore, y equals x squared is an even function, and its graph is symmetric with respect to the y-axis. Let's examine what it means to be symmetric with respect to the origin. If I start with the point 4, 6, we ended up replacing both the x and the y coordinate with its opposite. In notation, it says if f of x is equal to y, then the x value becomes negative and the y value becomes negative. So we can think about doing this in two steps. Replace x and y with their opposites. So if we start with f of x, we replace x with its opposite and y with its opposite. And if we end up solving for y by multiplying both sides by negative n, we get this relationship. Let's see what that means with a function that we know is symmetric with respect to the origin, y equals x cubed. Replace the x with its opposite, and let's call the whole thing negative. The y value is replaced with its opposite. Let's do some algebra. Negative x raised to the third power is negative x cubed. I still have to make that negative, which becomes y equals x cubed. This is the y value equal to the original. If that's the case, then it is an odd function, and the graph is symmetric with respect to the origin. Essentially what we're doing is we replace x and y with their opposites, do the algebra, and if you end up with the same as the original function, it is an odd function. Here's an example of one that is neither even nor odd, y equals x squared plus x, which we graphed earlier. If we try replacing x with negative x, we can do that, but we do not end up with the original function, so it's not even. If we try replacing x and y with their opposites, replace y and x with their opposites, do some algebra. I'm trying to solve for y. This is not the original function, therefore it is not odd. If it's not even and it's not odd, we're simply going to say it's neither one. Finally, we haven't talked about what it means for a function to be symmetric with respect to the x-axis. If you think about that for a minute, if a function was symmetric with respect to the x-axis, we would have two values of x, one value of x related to two values of y, which means it would not be a function. In other words, if a graph is symmetric with respect to the x-axis, it violates the vertical line test. Think about that.